All right, let's keep rolling. So I kind of want to quit, but I'm going to keep going. And now we're going to take a look. We looked at what is an interval estimate of a population mean when the standard deviation of the population is known. Now we're going to look at an interval estimate of a population mean when the standard deviation of the population is unknown. So if an estimate of the population standard deviation cannot be developed prior to sampling, we use the sample standard deviation S to estimate the population standard deviation. This is known as the population standard deviation unknown case. In this case, the interval estimate for the population mean is based on the t distribution. So we have the z distribution, right? Like this is the z distribution, z-score table. And we could also go to the t distribution table and just see what comes up. So here's the t table from San Jose State University. I like it. And I'm just going to close that calculator. And if we zoom in on this t table, cumulative probability, one tail, two tails, degrees of freedom is what that df stands for. Here's one tail, here's two tails. And then the textbook has its own version. I'm just going to compare this to textbook. Hold on. All right, so our textbook looks more, so the resources where we had San Jose and then we had Purdue, and this is what San Jose looked like, and this is what Purdue looked like. And if you look at when we're dealing with one tail and one degree of freedom and, the tail has 20% of the data, that's 1.376. And so 1 degree of freedom, 20% of the data, 0.2 is 1.376. But I like this better. This is what it looks like in the back of our textbook. And we even have this graph. And we're talking about this area right here is just upper tail probability. And that's what it looks like in the book. So we're not going to use the San Jose one, same numbers. But this is for one tail or two tails. And our textbook just presents one tail. And so that's the one we're going to work with here. And as a matter of fact, I'm just going to bookmark that. I'm going to put a big T next to it like that. And it's up here on my bookmark now. And I'm also going to bookmark this one. And I'm going to put a big Z next to it like that. And so now I got my T and my Z. So as we're going through this class, we could always just look back and forth between them. I'm going to put the Z first because you learn about that first. And then we'll have the T. All right. So in this case, the interval estimate for the population mean is based on the t distribution. And t distribution is just going to be just pretty much like z distribution. There's some differences we're going to learn about, but the way we go about it is exactly the same. There's a probability, there's some sort of a score, and just like we did stuff with z, we're going to do stuff with t. And we do t when the population standard deviation is not known, when it's unknown. William Gossett developed, whatever, pause the video, read about it. The t distribution is a family of similar probability distributions. So it's a family of similar probability distributions, similar to the z table. A specific t distribution depends on a parameter known as the degrees of freedom. And so we have more terminology. Don't you love it? Degrees of freedom refers to the number of independent pieces of information that go into a computation of S. ChatGPT, file, download, PNG, and then come in here and can you please explain degrees of freedom to me in simple terms. See slide attached from my textbook. And we'll attach that slide, upload, and we're looking for that one. Go, go baby, go, 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 go baby, go, 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 make me smarter, go. Degrees of freedom, often abbreviated as DF, is an important one in statistics, that concept, especially when you're working with the t distribution as shown in your slide. Degrees of freedom explained simply. In simple terms, degrees of freedom refer to the number of independent pieces of information that are available to estimate a parameter. Think of it like this. When you're calculating something like the sample variance or sample standard deviation, you first calculate the sample mean, average. Once you know the sample mean, not all data points are free to vary anymore because they are tied to that calculated mean. Degrees of freedom tells how many values in your data set are free to vary after certain restrictions, like calculating the mean, have been applied. Example, let's say you have a sample of 5 numbers and you want to calculate the variance. You first calculate the sample mean. Now 4 of your numbers can vary freely, but the 5th number is fixed because it must make the total sum equal to the sample mean. So the degrees of freedom would be n minus 1, where n is the sample size. I don't quite get that. Say you have a sample of 5 numbers. You want to calculate the variance. You calculate the mean. Now 4 of your numbers can vary freely. Okay, but the 5th number is fixed because it must make the total sum equal to the sample mean. Total sum equal to the sample mean. Total sum, sample. So the degrees of freedom would be, that doesn't make sense to me. So you have 4 degrees of freedom when calculating variance. Why degrees of freedom matter? Degrees of freedom are important because they influence which distribution you use to make inferences about your data. When the population standard deviation is unknown and you're estimating it from the sample, use the t-distribution instead of normal distribution. The shape of the t-distribution changes based upon the degrees of freedom. As your degrees of freedom increase, which happens with large sample sizes, the t-distribution gets closer to the normal distribution. In summary, degrees of freedom are the number of values in a data set are free to vary after calculating a statistic like the sample mean. When using the t-distribution, the degrees of freedom help determine the exact shape of the distribution. Let me know if you need further clarification. Yes, can you please further clarify the degrees of freedom by giving me an example illustrating Boom. Let's see what it does to that. I want to see like degrees of freedom are the number of values in a data set free to vary after calculating a statistic like the sample mean. Let's break it down. Imagine you have a sample of 5 numbers and they are blah, 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 blah. 4, 6, 8, 10. Now we don't know the 5th number, which is x underscore 5 yet. Calculate the sample mean, right? 4, 6, 8, 10 is 28. 28 plus x over 5 divided by 5 is equal to 8. Let's say we want the sample mean to be 8. We want the sample mean to be 8, right? Multiplying both sides by 5. So now we solve for 5. We get 40, 28, and then that 5th one, 40 minus 28 is equal to 12. So the 5th number has to be 12 to make the sample mean 8. Degrees of freedom. Now here's the key part related to degrees of freedom. Before calculating the mean, all 5 numbers were free to take any value. However, once we set the sample mean, which is based on all 5 numbers, the first 4 numbers can still be any values we choose, but the 5th value is no longer free to vary because it has to be exactly 12 to ensure the mean is 8. In this case, we have 4 degrees of freedom. The first 4 values are free to vary. The last value is dependent on the first 4 to maintain a sample mean at 8. So the degrees of freedom are n minus 1, where n is the sample size. Here we have, since we have 5 numbers, the degrees of freedom are 5 minus 1 is equal to 4. General rule, whenever you're estimating a parameter like the mean, one value is constrained by that estimate. So the degrees of freedom are the number of values that can vary freely, which is typically n minus 1. We see n minus 1 all around. Degrees of freedom affect many statistical calculations, especially when working with smaller samples and using the t-distribution. The fewer degrees of freedom, the more uncertainty there is in your estimates, and that changes the shape of the t-distribution accordingly. Does this help clarify degrees of freedom? It does. You're amazing. Thank you. And I'm just going to put in here, it does. You're amazing. Thank you. Boop, boop, boop. Let's see what it says to that. What are you going to say to that? You're very welcome. I'm glad the explanation helped clarify things for you. If you have any more questions or need further assistance, feel free to ask anytime. You're doing great with your learning. Thank you. Thanks. Thanks. Your help makes a difference. It's pretty amazing. It's a pleasure to assist you, and I'm happy to be part of your learning journey. If you ever need help again, please don't hesitate to reach out. Let's do this. We'll do that one. We'll do that combination there. What are you going to do with that? Glad you're happy. Take care and feel free to reach out anytime. It's hysterical. It's amazing. It's the best tutor I've ever had. You are so empowered to learn with this tool. It's incredible. All right, so basically what I take away from that is like I get some understanding, but I also am kind of like, all right, this is for like people who are getting their PhDs in statistics or their masters in statistics, and that's not me. That ain't me. That's not me. So I'm just basically saying degrees of freedom. That's beyond my pay grade, but I'm just gonna take that at face value. You know, got a little bit of insight into it. And so degrees of freedom. There we go. We did that slide. T distribution with more degrees of freedom has less dispersion. Okay. And as the degrees of freedom increase, the difference between the T distribution and the standard normal probability distribution becomes smaller and smaller. I think that's pretty important. So we'll just give it a little bit of a highlight. And so here is like, you know, 10 degrees of freedom. It's wider. And, you know, standard normal distribution is there. And then 20 degrees of freedom, it starts to approximate the standard normal distribution. For more than 100 degrees of freedom, the standard normal z-value provides a good approximation to the t-value. And the standard normal z-values can be found in the infinite degrees row of the t-distribution table. Is there an infinite degrees row? There it is, right? And so that is like, you know, for, I don't know, 0.05 in the upper tail, which would normally be 0.025 if we were doing 95% confidence level. There's the confidence level. I like this table, 95%. It's 1.96. And that's exactly what we got at 95% confidence level is in the upper tail. That's 97.5, and 97.5 is right there is 1.96, right? It's 1.96, and 95% confidence for alpha here, which is infinity. That's also alpha, by the way. Isn't that? No, that's just infinity. That's just infinity. 1.96 at 0.025 in the upper tail, right? Because that's exactly what the z gave us. So as you get more degrees of freedom, which is stuff that can vary, not quite sure how you get those, but they just give it to us in all of our formulas. Again, beyond my pay grade. But you know, as you get more degrees of freedom, you approximate normal distribution, and you could use the z-table, approximates the z-table. So selected values from the t-distribution table, we're looking at that already. And interval estimate of population mean, where the standard deviation of the population is unknown. And it's sample mean plus or minus the t all over the sample standard deviation divided by the square root of n. And that's the standard error. And so this is the one we had for population standard deviation known. And here's the one for population standard deviation unknown. So this was known, this one's known, and this one's unknown. So you can see this was the population standard deviation. This is the sample standard deviation. This was the z-score, this is the t-score. Okay, so that's the difference between standard deviation of the population known versus it's not known. So you're using the standard deviation of the sample. And the standard deviation of the sample notation is S, right? Sample standard deviation. So x bar is the sample mean. 1 minus alpha is the confidence coefficient. And so alpha is the tails. So the confidence coefficient is also like our confidence level. Confidence coefficient is confidence level. There we go, right? So that makes sense. And then we have t subscript alpha over 2 is the t-value providing an area of alpha over 2 in the upper tail of a t-distribution with n minus 1 degrees of freedom. And s is the sample standard deviation, and n is the sample size. Oh, so our degrees of freedom is just going to be the sample size minus 1? Is that right? Because the example ChatGPT gave us, if there's 5, we had like 1 degree of freedom, right? Is that the one it gave us? 5 minus 1. Oh, it's 4 degrees of freedom. So there's only one that's not free to vary. Only one that's not free to vary. And but we were varying the 5th one. So because 4 could vary, but the 5th one, it has to be determined. Once you're like saying you're going for 8 for your sample mean for whatever reason, like these 4 could be whatever you want. They could vary. They have 4 degrees of freedom. You have 4 degrees of freedom in here. This one, once you've determined this, And this, all that, right, this one can't vary, so that's not free. So your degrees of freedom are 5 minus 1, the one that can't vary. So as you get a larger sample size, right, n minus 1, 100 minus 1 gives you a higher degrees of freedom. It's 99 degrees of freedom. S is a sample standard deviation, and n is the sample size. Example, yay. Do you want to do the example now or do the example in the next one? Maybe we should leave that as just theory, and we'll do the example in the next video. Let's do that. See you in the next video.